Okay, so up until now we've been talking about quadratic functions and looking at the different ways that we can graph a function. So let's see how we can apply that in a real-world application. In this particular example, we're talking about a shot put whose path is shown on the graph. When it's released at an angle of 65 degrees, the height then that the shot put is going to take is modeled by the function given here, g of x, where x is the distance, the horizontal distance away from its point of release. So you've got to picture that you have the shot put person right here, and they are releasing the shot put. So this distance along the x-axis is how far it travels away from the point of release, and this distance here along the y-axis is how the height that it travels. Now this question, letter A, says, well, we want to know what is the maximum height to the nearest tenth of a foot that the shot gets, or the shot put gets, and how far is that from its release point? So what is the maximum height and how far is that away from the release point? So remember that on our quadratic functions we have an object here which is going to be traveling along, and when it reaches this point in here, whatever this point is, that's the maximum height it's going to get, and then it's going to come back down. So this question, letter A, is referring to what is the maximum height, so the y value associated with this point, and how far from its point of release does this occur. So how far is it going to be from where he released it? So we're looking at the vertex, or the maximum, what the ordered pair is for this point right here. So this would be the vertex, or the max of my function. How do we find the x and the y coordinates for that particular function? There's two ways for us to do it. The first way would be to recognize that this max is the vertex, and if I wanted to find the ordered pair representing the vertex, I can do that by simply using the vertex formula. X is equal to negative b over 2a. They gave me the function representing this path, so pulling out a's, b's, and c's, whatever we need from this, we can find out that negative b, which is 2.1, divided by 2 times a, which is a negative 0.04. When we plug that thing into our calculator to the nearest tenth, we find out that the x-coordinate would be 26.3. So the x-coordinate would be 26.3 for this spot. And then how did we find the y-coordinate? Well, we plug it back into the function and we evaluate the function at 26.3. So we would have negative 0.04 26.3 squared plus 2.1 times 26.3 plus 6.1. When you put all of that into your calculator to the nearest tenth, you find out that that's 33.7. So this is 33.7. So the maximum height of the shot put is occurring right here at 33.7. This is the maximum height, because remember, the y-coordinate, or the y values, are representing height, and then how far is it from its point of release? That's the x-coordinate. This is the distance from the release. Okay, so this is the distance from the release. This is the horizontal distance that it has traveled, right? It traveled this far horizontally, and it is going to max out at 33.7 feet for a height. Now the next part of this question says, what's the shot's maximum horizontal distance? Well, that's a little bit different of a question. If I think about the path that this shot put travels, then the maximum horizontal distance is how far did we get, this is the maximum distance horizontally, from where we started. So it's this point right here, which is the maximum distance from where we started. If that's the case, then if we're thinking about this point right here, then we want to know what x is when y is 0. Because I have the coordinate for that would be 0 for y, and I'm trying to solve for x. So if we have the function here, g of x is negative 0.04 x squared plus 2.1x plus 6.1, and we set that equal to 0. Well, up until now, how have we solved a quadratic function when it was set equal to 0? We want to either solve using factoring or the quadratic formula. Because really, can we even, I mean, to contemplate having to factor 0.04 using trial and error is just not really something I'm anxious to do. And I could use the quadratic formula using the a, the b, and the c that you are given here. But the other way for me to be able to do this is to go in and let's use our calculator when we are at this point now. So I'm going to put this function into my graphing calculator. Okay, so here I have my graphing calculator over on the left-hand side, and I already put the function on the y1. Now I want to take just a second because you may or may not have this plot up here. If plot 1 is highlighted for you, because let's say we've been doing a regression and you forgot to turn it back off. If plot 1 is highlighted and you're getting errors when you try to graph something, you want to make sure that you go up there and we turn it off. I do that by hitting enter, and then when I arrow back down, it should be off. There. Now my plot is turned off because it's not highlighted anymore, and I could look at on my own, I could look at the graph represented by that function we were given. The only problem I have with graphing this new function is I need to adjust the window so that I can see the whole thing. Well, if you come over here to the picture that was already given to us, I have an x distance that's going to go out to about 60 here, and a y distance that goes up to about 40. So I'm going to use that window to adjust the window on my calculator. So I set window equal to 0 for my x min, and the x max is going to be 60 like I said, and I'm going to scale it by tens, we'll call it. The y minimum value is 0, but the maximum is going to be 40, and I'm going to scale it by tens as well, just to be consistent. Now if I go graph this function, you can see that it is a parabola that's going to look a whole lot like the one that we have on the notes. The point I'm interested in is the point that's over here where it touches the x-axis. Now in order to get that point, the intersection of that point and the x-axis, I have to kind of do one extra step on my graphing calculator. I want to use the intersection option of my graphing calculator, but it has to find the intersection between two lines or curves. So we're going to let the second equation that we graph be y equals 0, because that is the horizontal line representing the x-axis. And when I graph it this time, you can see this red line that appeared now on my x-axis. So I'm just kind of trying to get the calculator to do an intersection for me. So when I want to know what the intersection is, over here at this point on the x-axis, I would do second trace. Number 5 is intersection. And I want to know the intersection between the blue curve, which has got a cursor on it, so I hit yes, enter. And now it has a cursor down here on the red line, so yes, enter. And I don't have a guess because I wanted it to tell it to me. And so when I find out what the intersection is, you can see that my cursor is over here kind of blinking, and that's where x is equal to 55.3. So this point over here is 55.3, or in other words, the maximum horizontal distance is going to be 55.3 feet. Now, how do you think I could figure out what was the height of the initial release? So in other words, what is the height here when I release it? Because notice it's not on the ground, it's up here. This time, thinking back to what that ordered pair stands for, I have 0 for x, but I don't know what y is. So I have a 0 for x and I don't know what y is. So I can plug in 0 for x into my function. In fact, let's look at that. So if I have negative 0.04 x squared plus 2.1x plus 6.1 is equal to the y. And if I let x be 0, then that just means, because these are going to go away, that means that the height at which the shot was released is at 6.1 feet. So that's how we can use not only our calculator but the function that was given to us to be able to find the vertex, the max, as well as these other points that were asked for in the problem.